Right. All right. I just want to take a couple moments here to introduce our featured speaker this evening, Dr. Ron Carson, who, after 27 years at the Boeing Company, retired in 2015 as a technical fellow. He's currently an adjunct professor of engineering at Seattle Pacific University and also a certified ESEP. So for those folks who are talking about certifications, he's an expert systems engineering professional. What I really enjoyed hearing was how much everyone loved going to Ron's talks, which is something that I've also enjoyed even before I joined the Seattle-Metro chapter. He's one of the most knowledgeable systems engineers that I know, and I always learn a lot after having a conversation with him.
Thank you.
And so without any further ado, Ron, I'm going to turn off and turn it over to you.
All right. All righty. Thank you very much. And let me get my slide sharing. So you should be able to see that. Okay, good. Somebody nodded their heads. That's great. So this meeting in June is the traditional NCOSE Papers Night. We canvassed for people who had submitted papers to the NCOSE Symposium so they could do their dry runs, but nobody had papers accepted. So I thought, well, I've got a lot of papers that I gave at NCOSE Symposia, so I thought, well, why not revisit some of those? Because as I've been giving talks on requirements, some of the concepts still seem to be new to some folks. So I'm going to sort of give you a retrospective. My LinkedIn profile is there, and I've got a YouTube channel, which I just named today, Ron on Requirements. People had said they couldn't find my videos. So I checked that, yeah, if you search on Ron on Requirements, the top thing that came back was the very first paper I did. So without further ado, let me press on. So let's see, here we go. So I've got a lot of references here. So we're going to be going through most of these, but they go back to 1995. There's a video in the YouTube channel on that. 1996, there's a video of that. Those papers led to the first paper I did on requirements completeness, and then structured requirements. And we continue to dialogue about requirements completeness with the working group report in 2004. We elaborated some of those concepts. Then I had a hiatus into system engineering measurement for about 10 years. And then got back into requirements, structured requirements, was issued 2 US patents in 2014 and was able to publish about that in the 2015 NCOSE Symposium, and then published some work I'd done with Robert Noel of the Boeing Company on requirements verification and validation. Since then, I had a video in the MBSE lightning round in the 2019 symposium, and that's also linked on my YouTube channel. And then a paper I did last fall for the WSRC, I gave earlier this month for the LA chapter, and I got the video of that listed here. So I'll be adding tonight's video into the YouTube channel later, and then you can watch these. All of the symposium papers are in the NCOSE Wiley Library, which is free for NCOSE members. So if you just search on my name under the symposia, you'll find all of these and other topics as well. So hopefully you'll find what scratches your itches. So what I'd like to talk about tonight, go back to some basic things. What is a requirement? You'd be surprised that there's been still this discussion about that. What do we mean by completeness? What do we mean by validated? And then how do we get to correct and valid requirements? And then onto the topic of quality measurements. And then a so what summary at the end. So what is a requirement? One of the first NCOSE papers on requirements, and I've been a member since '92, So that's almost 30 years. Rick Harwell from the Requirements Working Group at the time. If it mandates that something must be accomplished, transformed, produced, or provided, it is a requirement, period. So it's not design description, it's not goal, it's not desire, it's a mandatory provision. And that's really the only way we can make progress on understanding and implementing more sophisticated techniques about requirements. It might be described as a need if it's actually mandatory, and the latest requirements working group guides have parallel sections on needs. I have my own opinions about that, that it's maybe excessive, but as long as we understand that these are mandatory characteristics that can work. There may be keywords in your business industry that set off mandatory requirements, like shall. Must is entering the lexicon because of what the Supreme Court apparently decided a few years ago. But concepts like tradable requirements are oxymorons. If it's mandatory, it's not tradable. Requirement is an acceptance criterion, and we get ourselves in trouble in system development if we don't insist on that concept. And I had to actually go through this in the working group paper on completeness in 2004 because one of the working group members objected to that concept of mandatory. So there are other suitable words for things that are not mandatory, like should, if you have a goal or objective, and that's one thing that's taught at Seattle Pacific in their senior design class. Will, for the intent, for an intention, like somebody will do something on behalf of this or that or the other program. And if it's just a description, then just say is or will be. That's suitable, but there should be some special word defined up front in a specification that says when we use this word, that means it's mandatory, and we should not include things as requirements if they're really not mandatory. So that's a pretty basic thing, but it continuously needs to be revisited. What do we mean by completeness? Well, completeness means that there's nothing missing, and it's a subset of correctness. It's one of the types of errors that you're missing something. So it's a subset there, and applies not only to individual statements, individual requirements, but also to sets of requirements. And I've had a number of papers on these. Even my first paper, 95, much of the discussion, and I watched the video, was about completeness. So, but explicitly 1998, the paper I did, or the correspondence I did with Tony Schell in 2001, the requirements working group paper in 2004, and the paper with Bob Noel in 2018. Simply tracing to all the parent requirements or needs is insufficient because the set of parents and needs may be incomplete, and it typically is. Sometimes it's in conflict with concepts of operations and other things. So how do we develop and ensure completeness? Well, so this is a graphic out of my first NCOSE paper. And formally, no functional requirement is complete unless there also exists another functional requirement, or more than one, whose union of antecedents, A union not A, is the universal set. What that means is you have a requirement for every possible condition of the universe. And you're going, how can that be right? Well, hang on, we'll get there. So that's the only way you can prove completeness, that no matter what happens, you have a defined behavior. And if you're missing a defined behavior for a certain condition, then by golly, either software or system test is going to write a problem report eventually on what you forgot or didn't get to or didn't think the system would ever experience. And I wrote this paper after a couple of years on a Boeing program where I was confronted with those opportunities from software and system test to come up with, well, what do you want the system to do under these conditions that we conceived in our software or found in our fault injection testing and system test? Wasn't necessarily fair, but I had to disposition problem reports, and I finally decided to quit chasing the design and the testing and come up with a method so that within the specification, all situations are covered. And the key to that is this diagram, that I have what I want to do, the A, and then I have everything else. So that's an else condition. If anything else happens besides this, then I want you to do something else. Might be continue to do what you've been doing, stop all execution, do something else in particular. It's very useful, for example, for safety conditions or invalid inputs. You know, they're out of range or whatever. The other thing we tumbled to is that defining the behaviors is going to be subject to agreement by the stakeholders. So the key for requirements completeness is you appropriately identify who the stakeholders are, and then they have to agree that the behaviors you've come up with, for example, for all these not A conditions that they never thought about, by the way, are the ones they're willing to live with. So it's more complicated than simply tracing to the requirements you were handed, because those are likely incomplete. And therefore, you're going to have to effectively invent acceptable and mandatory behaviors for other conditions. So it's not just enough to trace from the parents. And that's commonly missing in our general understanding about how to do requirements, because we emphasize traceability and you got to do parent-child flow down, but you may still be missing things at the top level. What do we mean by validated? And I'm sorry the title came out wrong in some of the publicity. That was my fault, so I apologize for that. So talking about complete and validated requirements. And the handbook version 4, by the way, there's a version 5 coming out. I don't know what the schedule is, but ensure that the system or any system element, and in this context of this discussion, a system element is a requirement, that it meets the needs of its stakeholders in the life cycle. So we're going back to the fundamentals of what it means to produce an acceptable or validated system. So we have valid requirements. That means we have only correct requirements, that they are correct and complete. That's a language out of ARP 4754A, which is about systems engineering commercial airplanes. And we have no unnecessary requirements. So complete meaning nothing is missing, and correct meaning nothing extra is included, and everything that's included is correct. And if we have that, then we'll really have the acceptance criteria for the system and the collection of requirements. And one test for that is if we check our requirements against the stakeholder measures of effectiveness, that's the MOES, and their needs and their concerns, that all of those are satisfied. Uh-oh, did we lose me? I look like I'm still in the meeting.
You're still here, Ron.
Okay, I just saw a note from John. Okay. To make sure everything that the stakeholders, and that's not just the customer, that's the public that has to live with it, and the developers, the suppliers, the acquirers, the users, the maintainers, that their needs, their measures of effectiveness, that those minimum mandatory criteria are satisfied. And then anything beyond that, goals, desires, and objectives, these can be handled as value propositions. What's it worth to have, say, an increase in range or an increase in quality or an increase in speed. Yes, there's a minimum, but we might be willing to pay more to get more. But that's a value proposition, and it's related to but different from the minimum acceptable. Another thing to pay attention to is that we have no unnecessary requirements. I got a question at the tutorial last Saturday for the LA chapter. Somebody said, I work for this company, we have thousands of requirements for low-level components. Is that too many, or do you see that in other industries? And we dialogued a little bit. It turns out they're imposing lots of design requirements. And it wasn't obvious that all of those are really mandatory, because it may be that someone who is writing the requirements, or that organization, is simply over specifying the solution, narrowing the solution space by essentially dictating the design via requirements. Well, that's not good systems engineering. And I tell my undergraduate students, we want to have few requirements that satisfy the stakeholder MOEs and the needs, but beyond that, leave the solution space open. So try not to use design requirements, try not to over constrain the solution, because you narrow the range of possibilities and it drives up cost. Managing and then verifying requirements is very expensive. So, I mean, it's of order of thousands or tens of thousands of dollars just to manage a requirement over its life cycle. So you shouldn't have unnecessary requirements just from a business standpoint. But we sometimes like to impose our favorite solution in the form of a requirement to make sure we get what we think we want, but that's not necessarily what's needed. And it likely is something other than the minimum acceptable characteristic for the acceptance criteria. So what do we mean by validated? Well, what we tumbled to is that we mean correct set of correct requirements. The aviation industry uses correct and complete. We've seen correct, complete, validated, but an operational definition is correct set of correct requirements. That is, each requirement is correct and the set of requirements is correct. And the set of requirements can be correct if and only if it includes only correct requirements and no unnecessary requirements, whether correct or not. So when it comes to errors, the correct type 2 error is no missing information. That's the completeness check. Nothing's missing at the individual requirement level, nor at the collective level. So each requirement is verifiable, meaning it's sufficiently clear and complete to be able to prove that it's needed, sufficient, and feasible. Because if it's not clear, you can't assess what it says sufficiently to determine sufficiency or feasibility or even necessity, because it's ambiguous, for example. Sufficiency, if the requirement is satisfied, then the parent requirement or need will be satisfied, and you can demonstrate that, perhaps sometimes in combination with other child requirements, because there may be a decomposition going on. But you could prove this analytically and eventually by demonstration. The other type of error, the type 1 error, is that there's no erroneous information. That is, every piece of information, whether it's timing or other performance values or functionality or interface identification or condition statements, it's all correct. So one way to test for that is the necessity criterion, that the parent requirement or need cannot be satisfied without this requirement. In other words, if I attempt to delete it out of my database, I'll find there's a parent requirement that goes unsatisfied. Or if I modify a characteristic, then I will find I can't satisfy a parent requirement or need. This also allows us to test for necessity. For example, we often see duplicate kinds of requirements in different sections of a specification. Well, what happens if you delete one of those? The answer is you just saved money, because you're still able to satisfy a parent requirement or need because there's a duplicate requirement. The feasibility check is a means for assessing that you can actually satisfy the requirement in implementation within the program constraints, that's budget and schedule, with acceptable risk. There's no guarantees about the future, but you need to understand whether the requirement is demanding that you build something out of what we call unobtainium, or it violates the laws of physics. And then it doesn't matter how much money you throw at it, you're never going to satisfy it. So we have these 4 checks, beginning with verifiability, sufficiency, necessity, and feasibility, as a way of ensuring correct set of correct requirements. And we found these to be disjoint, concise, and complete. That is, they are necessary and sufficient to determine correct and complete. These were contrasted with the 14 requirements characteristics in the requirements working group, Guide to Writing Requirements, which have a lot of duplication and ambiguity, and you can read our 2018 paper to see our comments on that. So this is how we get correct set of correct requirements as our definition of validated. So how do we get there? Oh, so we use these concepts as a means to make progress. So we're decomposing what we mean by validated, and this will allow us to get to structured requirements, another decomposition. So like in most things in the sciences and engineering and complex problems, we make progress by decomposing. So we take a concept and we break it down into manageable and measurable pieces, and then we can make progress on a solution. So how to get there? Well, we started with the idea of a structured requirement. I began working on this in my very first NCOSE paper, looking at the condition statement, and found that condition statements were largely excluded from requirements, yet they're absolutely necessary for determining when a requirement needs to be exercised. Could be phases of the moon, it could be states of the system, it could be different environments. But if you don't know the condition, could be a specific triggering event. You know, you don't want it always be sending a message. You might want the system to send a particular message in response to something else. So I started getting involved in this idea of structured requirements back in the 90s. And then the 2001 paper got into it some more. And then we formalized it over the next 10 or 12 years. So first thing you have to figure out, well, what's the target format? Because this is going to determine the data you need to populate the requirement. And then from that structure, go figure out, well, where am I going to find the information for each element, each of those elements of a structured requirement? And how will I know that that information is also correct and complete? And so we started applying something that I learned early in my systems engineering career in the early 90s, and lots of organizations have taken credit for it. I think I first published a paper using it back in 2001, but lots of organizations have taken credit for this, but not enough organizations actually use it, unfortunately. The who shall what, how well, under what conditions. And we've used this in statements of work and contracts. You think about it, it's, well, who's got the action item, or what entity is performing whatever it is, or has a particular characteristic. That's the what. It's either a function or a characteristic. The how triggered event. So, but why is this the correct content because it's necessary and sufficient for verifiability. If I have a requirement that states all those things, I can confirm or prove false a claim that a particular requirement is satisfied. If I'm missing any one of these things, then I can't say one way or the other. Like if I'm missing a condition statement, the supplier only has to come up with one condition of the universe under which their system satisfies the other aspects. Like the example I used in 2001 was how fast my Chevy could go. The requirement that I proposed was 80 miles per hour. And I said, well, my Chevette could only go 80 downhill in a tailwind. But if you didn't include a condition statement that said level ground with no wind, the manufacturer could claim that they satisfied it because they could show that it went 80 downhill in a tailwind. And that may not meet the need or the intent, but it satisfied the letter of the requirement because it was missing the condition statements. Similarly, if you eliminate the how well, the airplane shall fly. You know, I got paper airplanes that do that. And then there's fighters and commercial airplanes. They all meet that functional requirement. But when you start getting into payload and range and reliability, the how well aspects, now we start differentiating valid from invalid potential solutions. So the who defines the responsible system or organization. You know, we are allocating this requirement to this component. The what is the mandatory characteristic or the behavior. What's it got to do, or what must it be? Like it has to weigh a certain amount, or less than a certain amount, or more than a certain amount, or it has to be painted a certain color for some reason. We talked about the how well and the under what conditions. So from this, we realized that we needed different structures for different kinds of requirements. And I've seen as many as 17 different templates in other papers and tools. We settled at the Boeing company, or I settled the Boeing company on 4 different types that I described in the 2015 paper and in the patents to reflect this pattern, but with more detail for the kind of requirement, like the functional performance requirement. And we combine function and performance because a function without performance is missing the how well. And so unfortunately, the C box still includes a functional requirement type, and you can imagine that it's not a verifiable type. I'm hoping the requirements working group will excise that out of the latest guides. But the last draft I reviewed still had it. So watch for that. If you have a functional requirement that doesn't have any performance, is not verifiable. This type is predominantly used for mission-oriented characteristics, what we want the system to do, its reason for existence. It also includes interface requirements regarding inputs and outputs, because any valid function must be observable at the boundary of the system by some manifestation, typically some sort of result or output. Design requirements that we typically major in, because we love to write design requirements, how to make it. These are constraints on the solution. Parts, materials, processes, physical allocations, or how we're going to standards or constraints on how we're going to implement the interfaces. Suitability types are really non-mission specific characteristics that address fitness for use, like safety, many ilities, different life cycle phases, transportation and storage, for example. And then I stewed about the last one here, the environment. And even though it really is primarily a condition statement that's applicable to all the others, I decided that was probably a bridge too far in trying to get rid of it, because it's got typically a whole section in specification templates. So I said, well, let's keep that, focus on the condition statements that may be related to different states and modes or different functions, but you have to describe the characteristic, the what, in the presence of a particular environment. So from that, we detailed out each of the types and realized this basic pattern, the who shall what, how well, under what conditions. And this is a graphic out of the patents. But it's got the 4 different types, and then all the elements associated with the various types. And we don't use all those elements on every type, but they're color coded in this presentation so you can see. For example, the functional performance type has the most elements, and these are colored in green, and I apologize if anybody is color challenged and can't see that. The agent shall function in accordance with interface output, so that's the constraint on the interface. With performance, that's the how well of the function, and then any timing when the output comes with respect to whatever the event trigger is, the initiating event, and its interface constraint, while in conditions. So you see the mapping of the colors in this detailed requirement structure to the basic pattern up here. So that's the functional performance type. The design requirement type is shorter, but we include some optional characteristics. It might be an absolute condition: the agent shall exhibit a certain design constraint. But there may be performance elements, like if you're talking about weight or color, you might want to designate a performance attribute. And there might be a condition statement like dry weight or empty weight. So, but we made those optional in this construct because we realized there's some things that are just absolute. But even something as simple as how big, dimensions, you might have to specify a temperature condition to ensure fit in your system. The environmental requirement details out, well, what the characteristic is. Like, it has to operate and satisfy all the other functional requirements during and after exposure to a particular environment. So that's a particular natural or induced, impressed or imposed environment. And there may be an optional exposure duration, like you're exposed to humidity for a certain period of time or whatever. And then the last type is the suitability requirement type. Again, it has a characteristic, but these might be more specific, like related to safety or availability or reliability or maintainability or transportability, with a certain performance attribute and a mandatory condition statement. So this is almost getting to look like the functional performance type, but it's missing the inputs and outputs kinds of things. And it addresses the whole entity. We talk about the reliability of a system. We don't talk about its outputs so much as we just say it's got to be able to do everything without breaking, with a certain performance attribute for a certain duration while it's exposed to certain conditions. And there's where you get, for example, the condition duration. How long is it exposed to whatever? So together, we get the 4 types that we say that these completely cover everything you might want to do in terms of requirements. We did a parallel analysis on statements of work before I left the company and started working on that as well. So, but the idea is you write something that is a technical contract where you can determine whether it was satisfied or not. And I was hoping that SysML version 2 was going to include something about structured requirements, but as far as I understand, it does not. So a requirement in SysML is still a single sentence without a defined structure. There are some tools that are on the market or maybe coming on the market that do this kind of thing. And good news is they are now linking these to their architectural models. So this is where the data comes from. And I'm going to show you an example of this for the tool I use in my graduate class at the University of Washington. But everything I'm going to show you about the implementation here is tool specific. And I go into this in more detail in the WSRC paper that I gave last fall. But these are based on the available classes, data types that are in the core tool from Vitek. So these are some of the ones we use in my graduate class when I have my students write their requirements and do their architecting and modeling. The agent, this is the who is doing what, or has the characteristic, has two classes depending on whether you're an operational perspective, in which case it's performer, or system perspective. And there we are, there we have the architecture framework rearing its very ugly head to say, oh, well, we need two different data elements because we have two different perspectives. That's a sad reality of the architecture frameworks. And there's even a third one now called a service in addition to systems. But that's the way those things go. So the architecture frameworks can be useful, but I think they're overly complicated. But you have to know what the data classes are in order to be able to populate the requirements. So if you're writing an operational requirement, you would use the performer class and its related operational attributes. If you're writing a system or subsystem requirement, then you would use the component class and its related classes, data classes. There's no separate data class for the keyword. So that would be something that you just have to define and insert when you're writing the requirement. Could be shall, could be must. I always tell people, well, put a paragraph up in section 1 of your specification to say, what is the mandatory word? And then what word indicates a mandatory characteristic? The function, we use 4 different classes, 2 in the operational perspective. The operational activity is like a function, and then there's the output, which is an operational item. In the system perspective, it's a function and its companion output, an item. So items and operational items are things that become inputs and outputs. They're exchanged among system elements and among functions. The interface output is the constraint on the observable manifestation of the function, represented as a link in the system perspective or a need line in the operational perspective. The performance attribute, it's a measurable attribute of the observable function, and it's not a separate data class. So depending on the tool you're using, you might make it an attribute of the function, as in core, or you might use a parametric diagram in SysML. Probably not going to get into that in detail in this presentation, but you can see the detail in the 2020 paper. The conditions arise from several possibilities. A state, and so there's a state class that you can use. The inputs and the inputs to that might be triggers, either continuous or triggering events, either the operational item in the operational perspective or the item in the system perspective. The event trigger is what starts the function, and it could be, again, an item or an operational item. The interface input is the constraint on the item or the interface item or the operational item, and therefore it's the link or the need line, respectively. The timing is an attribute of the function, so it's not a separate class. The design constraint might be a characteristic that's derived from a measure of effectiveness, a capability, a concern, a risk, whatever, but it's something that is in the model so that you know it's not just a choice of the requirement writer, but it's actually traceable to something that's a need. The characteristic might be something that the attribute is, has, or does, used for the suitability and environment types, might be derived from a function or a capability, a measure of effectiveness, or an operational activity. And the environment exposure is a duration associated with the input, and in core you can make that an attribute of the item or operational item. So depending on the tool you're using, you can capture, you can map the data elements of the tool into the data elements of your structured requirement, but you have to know what your organization is using for structured requirements. And the last one is the duration, which is an attribute on the item. So example of how we do this mapping, and this is a functional performance requirement using the requirements diagram, which is a standard feature of the SysML tools, although this one I've customized. We have the requirement in the box up here. It's a sentence. We have the function it's related to. So the requirement specifies the function because it's got the performance attributes. And in the function, we indicate several things. One, we show where it's derived in the model. So here's our function in the FFBD or activity diagram. And you see it's got inputs and outputs. And we show those on the function diagram along. So we've got the inputs here, the outputs there, the parameters associated with accuracy and reliability and duration. There's our timing. So all the things I need, I can find, and then I can use them to populate the requirement, the function, the interfaces, the inputs, the outputs, the performance attributes, the component, which is the who, make sure all that agrees and lines up and I haven't made a misallocation. The condition statement, here I've got the state condition listed. And then I can check that my structured requirement actually satisfies the template. So this is a tool for writing good requirements. And the methodology is that we want to derive that content from analysis. We start with the stakeholder problem. We don't start with the requirements because where did the requirements come from? Well, they came from somebody thinking about, well, what's the problem? What's the need? And how are we going to resolve that? Too often, we just decompose requirements. And when we do that, we end up with requirements that may not agree with the need, may not satisfy the need in terms of functional capability, measures of effectiveness, and other constraints. So we use our analyses to drive out the functions, the interfaces, the performance, and then we define the requirements at each level from the analysis. So this top level is indicated this way because sometimes you get requirements and you have to reconcile those to other statements of needs, like a concept of operations. So I put reconciliation up here for the condition when it's not actually derived, but at each of the other levels, left to right, we derive the system requirements from the architecture and analysis. We validate the system requirements based on the architecture analysis, and we trace the requirements back to the architecture and analysis and to the parent requirement. And we can apply that at each level. And I argue that elicitation is a poor substitute. One of the dominant practices, and if you look in the literature of the last 30 years, it's about requirements elicitation. Let's ask the customer what they want. And typically a customer wants a solution of a certain type. And so I never ask clients for their requirements. I always ask them about their problems and how they measure success. And from that, I will compose requirements on whatever their system is, operational or otherwise, and say, in order to satisfy your problem, these are the requirements you must have. And if all I did was elicitation, then I would be taking dictation. And when I put together, then somebody put together a system that met those elicited requirements, it might not solve the problem, probably wouldn't satisfy the need, and the client would be very frustrated. Like, why did we go through all this? We didn't get what we needed. So say elicitation is a poor substitute for analysis, principally because most stakeholders will think in terms of solutions rather than needs, unless you can educate them. So I don't ask about requirements, I ask about problems and measures of success. If we solve your problem, how would we know? What would we look for? What would we observe and what would we measure? And what would we find when we measured? So that's a key item. So something to pay attention to in the NCOSE requirements working group guidance, the guide for writing requirements and the guide for managing needs and requirements. They formalize needs as well as requirements. I don't. I think formalizing the needs is an extra step. I'm willing to accept somebody's statement of a need, however they're willing to state it. And just then I'm going to dig into whether it's a mandatory characteristic the way they've stated it, or it's just a wish. So how do we ensure completeness? So here's a couple of steps. Having derived the requirements from the concerns and the scenarios and the MOEs, are we complete? And you already know that the answer is probably not. So those are necessary, but not sufficient to guarantee that, because as I said earlier, completeness is about defining the system behavior and characteristics for all possible conditions of the universe, which is, yeah, it's an infinite task. So what can you do realistically? This is the else condition I alluded to earlier. So this is a slight modification of the original diagram from the first paper. But normally we would describe functional behavior, and I realize I'm going after 7:30, but I got a late start, so I'm going to exercise my right. Sorry about that, Ray, but I'm going to have to continue. The go path, on this condition A, do function 1. And we seldom ask about the non-go path, the else condition. On not A, on condition not A, do function 1B. That's the addition that now this combination guarantees that at this point in the operation, no matter what happens, I've got a defined behavior. If I have A, condition A, I do function 1. If I have anything else, I do function 1B. It might be keep doing what you were doing before. It might be stop. It might be shut down, whatever, but you have the opportunity to define that. And defining these is why the stakeholders will have to get involved, because they didn't think about this condition. And it gets more complicated, of course. So this is out of the 1996 paper. How do we determine the subordinate conditions of interest? What if not A actually has several different things, some of which are explicit? D here is still the else condition. And this was the question I got at the very first time, first few times I gave that original paper. How do you determine these conditions? I said, I don't know. And then I figured it out in a discussion in the van on the way back to the airport from the first symposium. And I couldn't wait to get home and write up the new paper. So 1996. So you analyze the interfaces across their parameter ranges. So here's where the boundary comes in. What are all the inputs? And what are all the valid ranges of parameters? It's okay between in the hashed area, any place else it's not okay. So now what do? Well, we define the behavior for all of those conditions and combinations. So a 2-parameter condition, say if both inputs P1 and P2 are valid, then you have a valid result. Otherwise, it's some shady thing. And you got to figure out how you're going to handle those in terms of else condition. And there's different combinations and different ways of writing that. But the important thing is you considered, well, what if I don't have the go path condition? What do I want to do? Is it an unsafe condition, for example? And therefore I need to do something else. So for each new condition or combination, you have to propose an associated behavior in the performance and then validate it with the stakeholders. You may have a good idea, but they probably haven't thought about it. So it really does come back to the stakeholders have to agree with the behaviors you define for all these conditions they didn't think about. And I'm not blaming them for not thinking about. That's why people hire systems engineers to think about these things. And then you have to iterate as necessary during the design activity, because you may come up with more detailed parametric conditions or combinations, but we want to do this ahead of the build and the verification. So we don't have to go redo the software or redo the hardware like we often do because we discover a condition during verification that is unacceptable. And now we have to define it in the requirements. So that's all rework. We want to get rid of that. And then once we've got these defined, then we want to validate it in the architecture model. In other words, run the simulation to make sure that the system actually behaves properly under those conditions. So again, we're using decomposition of the condition statements on the various parameters to make progress in defining the system behavior. Once we have the elements of a system, then we can start measuring whether they're correct and complete. So we applied this concept of closed loop feedback control, and this is a graphic out of the INCOSE measurement primer from 2010. If we have requirements in their parts, we can measure, is this the correct agent? Is the function observable? Is the interface defined? Is the performance defined, and are the tolerances appropriate? Is the timing identified? Do we have a trigger? Is the interface defined for the input trigger? And do we have a condition statement? And in the Boeing construct, we used a graded scale from 0 to 4 in the requirements quality measurement for each of these elements, and we could get a synthesized score for each requirement. We would first type it, is this a functional performance requirement or design or environment or suitability? And then based on whatever type it was, then we would look for the different elements and then grade the quality of the elements. That's a lot more granularity than a lot of the initial requirement quality measurements were, which are just a 0 to 1 kind of a score. And we actually automated part of this in our doors tool, where we wouldn't allow the requirement author to write a whole requirement. They would have to select the type, and then we would display the pattern that they would use to model their requirement after and all the applicable fields. And then they would fill in the fields, and then we would concatenate the fields to construct the requirement according to the model, and then show them the requirement and then give them a score, requirement quality score. Like, you got the wrong element here. That's not the right name of a system. Or you don't have an observable function, or you're missing a constraint on the interface, or there's no performance attribute. So we had done some automated scoring just to get a preliminary idea, but we constrained the requirements engineer. They couldn't alter the final text. If there was a problem with the text, they had to go back and change it in the individual fields. In other words, we enforced a structure on the requirement, and people didn't like that, of course, because we like to have a little bit more freedom, but it was effective in ensuring, improving the structure of the requirements and getting people to pay attention to the content to make sure they had all the necessary elements. Another way to do the validation is by simulating the model. So we don't simulate the requirements, we simulate the model that's behind the requirements. And the tighter you tie the model to the requirement, like auto-generating the requirement from the model, which we didn't get to while I was at the Boeing company, although we had designs for it. You can simulate the model to see that you've got sequence, control flow, inputs and outputs, connectivity. So the basic elements to ensure that if we actually built a system according to the requirements that were derived from this model, then we would get what we needed in terms of time and performance and information or other things get from one place to another appropriately. So that's sort of the summary of where I've been over the last almost 30 years in requirements, and it seems to be new for many people, even many who've been around a while. So I appreciate your attendance. So why is this important? We want to develop requirements from other things. We don't just start with requirements. So some rationale, some reason for existence of this system that's based on concerns, measures of effectiveness, concepts of operations and maintenance and test, missions and the functions derived from those, and the various inputs and outputs in the context of the system of interest and the performance attributes. When we have all those things, then we have the data that enables us to write requirements, but we derive the requirements by analysis, and that inherently gives us valid requirements, or at least more valid than if we didn't derive the content from analysis. We use structured requirements as templates to define the data needs for each requirement type, and that forces us to go back and do the analysis to find the data. Well, what is the function? What is the performance? Where are the inputs coming from? And what do they look like? And where's the output going? And why do I need it? And does this line up with the concept of operation, for example? We can validate the results by deriving the requirements from the analysis and by simulation and by getting stakeholder approval, not just to the requirements, but to the behaviors we're expecting, and ensure completeness by treating anomalous conditions, the things we hadn't thought about, and the else conditions. Then validate those results with the stakeholders, because it's really only the stakeholders that can agree that you've captured the behavior they're wanting in your system. So with that, I'm sorry I've run long, but I have time to take some questions. So if you want to verbalize or type them in the chat window, however. Anybody? Questions?
I have a question, Ron.
Yeah, go ahead.
This is John Palmer.
Yes.
Recently come upon an expression referred to as most important requirements as a term of art, perhaps, describing a certain class of requirements that need additional attention. For one, is that expression familiar to you?
Oh yeah, I've seen that for 20 years.
So there's of course, some contention around that expression because it gives an impression or an implication that some requirements are more important than others in terms of their need to be satisfied. But of course, we would say all requirements equally need to be satisfied. However, there does seem to be some use for recognizing complexity or the challenge of satisfying some requirements over other requirements. So I wonder if you would talk to that at all, what you've encountered, any insights you might have about better terminology or anything like that.
Well, yeah, I've seen that. It's also key performance parameters, key system attribute, something that indicates there is an additional class or characteristic associated with some requirements. The problem is, as soon as you say most important, that means there's a subset that are least important, which means they're effectively tradable. So I appreciate the concept, and you might say, well, only the mirrors are true requirements and everything else is not. That's one way of looking at it, although I have yet to find a customer that will admit that. But that's effectively what they're saying is everything else is tradable except the mirrors, the most important requirements. So you might adopt a posture that says, we're only going to worry about satisfying the mirrors, and the others may or may not fall out, and we'll, sue for mercy or something. But it is a conundrum because it basically creates an oxymoron. A most important implies a least important, which is another way of saying they're willing to give it up for whatever reason. That might be appropriate when you're doing a acquirer funded development and they're not sure what it's going to cost and they're not sure what the value proposition is. So they start running out of money. There might be things they're willing to give up. Makes no sense on a firm fixed price, because if I'm an acquirer, I say, well, yeah, I want it all. Well, if you want it all, then don't call some things mirrors, because you give the impression to the supplier that you're willing to give something up, maybe for consideration, but you're willing to give something up. So it's a troubling expression. It's commonly used, but it points the finger at not at the idea that, well, not all requirements are really requirements. And some things maybe we want to exercise some value analysis on. So great question, by the way. Thank you. Somebody else?
I have a comment in that regard. Can you hear me, please?
Yes, John, I can hear you.
Yes. As I said earlier in the introduction, my field of specialty is a little bit different from the aerospace and high tech. It's heavy civil construction. For example, I've done a lot of work in dams and hydroelectric power plants, and it's a different culture from what many of you are used to. And a phrase that I run into over the last 30, 35 years is very simple, or very similar, Ron, to what you just described. Folks will write specifications and they'll add the word strict. There are things that are supposed to conform to a specification, and then they want something that strictly conforms to a specification. And my observation, Ron, is the same as yours. You just set up two levels of conformance to the requirements.
Yep.
The strict stuff, that means, oh, we really mean it. Well, that implies then that if you don't require strict conformance, that conformance becomes, from my perspective, mostly optional.
Right.
And that's not a very good way to specify a system. The challenge in my environment is that I'm dealing with people who are virtually clueless about these basic principles of systems engineering. So I have to figure out how to do it. It's a cultural issue that it probably occurs everywhere, but more often in my type of work. So, Ron, I appreciate what you said. In my experience of about 40 years and then 45 years in engineering and construction, that's very valid what you just described.
Thank you. Well, thank you for your comment. Yeah, and when we introduce these adjectives, then we're bastardizing the word requirement and making it no longer a mandatory characteristic, but something else. If we have the need to insert this adjective like strict or most important. So as John said, when you see that, that's a clue that there are things in there that really aren't necessarily requirements. And it's useful to ferret those out and gain an understanding of the value proposition for each of those that's not a most important, because maybe you can just get rid of them and save the program oodles of money, maybe. Another one?
I'm sorry, I would like to clarify maybe another interpretation, and perhaps you have a better way to express it. Most important in the sense of, because it's a difficult to achieve requirement, needs particular attention by chief engineer or program managers during development as a way to make sure that requirement comes home.
Well,
so I wonder if
okay, that's a different flavor.
Yeah, so yeah, exactly. And I'm wondering, I don't know if you come upon that, and if so, or even either way, whether there might be a better way to characterize it.
Well, that becomes a requirement that goes into the risk program, right? Because now you have a feasibility issue. So in the process of doing validation on the requirements, this should pop up as this one's at risk from a feasibility standpoint, given the constraints of the program, technology, maturity, schedule, budget, whatever. So boom, it goes in the risk program. But that's not because it's a mirror, it's because it is higher risk when you do the feasibility assessment. And that's why the validation activity is important, to say, you know, what's the feasibility, and is it putting the program at risk? But I wouldn't, you know, that's, to me, is not an appropriate use of most important. This would be a most at risk, or this would be, you know, risky for the program if it's not satisfied. But that's not a most important requirement. That's just a risky requirement. That's the way I look at it. But that's why you do validation with those 4 criteria.
Hey, Ron, this is Paul Van Tolde.
Yes.
Can you shed a little bit of light between the 4 types of requirements? Is there guidance, or maybe these are sniff tests on what's the relative percentage of requirements? Should you expect a large maturity of your requirements to be functional requirements? What do you do if, maybe this is part of the customer needs analysis, if a lot of the requirements you get are more design constraints?
Well, you had about 6 questions in there, Paul. So the guidance would be, well, you're in the Boeing company, so John Palmer can show you the business process guide that he originally authored, and I did the revision for, that goes into detail and all this stuff. I mean, massive detail on how to write each clause. As far as the weighting in a spec, I'd say specs are overweighted on design requirements. One of the reasons is the way they're developed is we copy the last spec that we had in our desk or on our server or in our account, and then add all the new things that the new customer wants, but we never get rid of the old design requirements. So we end up with hundreds and hundreds of extra design requirements. One program I went through this kind of analysis, it was about 11 years ago. And we evaluated all the requirements, and most of the requirements were design requirements, and we said they could get rid of 40% of the requirements in the spec because they were duplicates. They were worded slightly differently. They may have used different design constraints, but they were addressing the same characteristic. So I would say we overweight on design requirements too much. I think environments, we probably were okay. Suitability, probably about right, from what I've, on average. Functional performance, probably too many because we separate function from performance. So sometimes too many and sometimes not enough. The test, in fact, people have told me, my functional requirements are too detailed. Well, show me where you can't observe this at the boundary of the system. And this is where we probably don't do enough work, because we write, I'll use the phrase high level type requirement, which expresses an intent, but isn't actually verifiable because it doesn't get down to the details of when you get this input, deliver this output. A transformational or transactional type of requirement. Input and condition leads to output, period. We don't have enough of those. We have aspirations in our functional requirements. I want the airplane to fly. The airplane shall fly. Not a useful requirement. But we probably have more of those than of the payload range kind of requirements for aircraft, or the payload range kinds of requirements for automobiles, or the payload range requirements for construction equipment. We have aspirations about, the system shall carry stuff. So probably not enough detail in the functional requirements, or the wrong kinds of functional requirements, even if the count looks large. But that's just a, quick feedback.
All right, that's helpful. Yeah, I think you're pointing to, really emphasizing the analysis part or of the task, and putting enough resources on it.
Yeah, if you want to lean out a spec, I just dive right into the design and construction section. Say,
Okay.
why do we need this? Why do we need this? Why do we need this? What if we get rid of this? Where's this come from? Why is it here? And you just got to be ruthless, because most of them are not well founded. They're vestigial from, who knows, 40 years ago.
All right. Good advice. Thank you.
Yeah. Okay.
I would like
Anybody
to comment
else?
on that, Ron.
Yeah.
You mentioned trimming specs and cloning project specs from old projects.
Yeah.
I've had some experience in that regard in heavy
sure
civil
you have.
construction.
Sure.
I was working for a manufacturer meeting some equipment requirements on a really big, heavy civil construction project designed by a world-class design company in that field. It's a very large international engineering company. And one thing I'm familiar with very thoroughly is welding, and their welding spec referenced a welding code that's been out of print since the 1950s. I think it was last published sometime in the 50s. Yeah. It became obsolete in the mid 60s. Mm-hmm. And what is obvious is that whoever was working in that company they just cloned the spec from a previous job, and decades go by and nobody ever bothers to take a look and see whether any of that stuff's available. I have a lot of feet of welding codes and standards, and the one that they referenced, I actually didn't have a copy of because it's so obscure. And that happens a lot in my particular field. So you got to be careful cloning. If you're going to clone a spec, you got to go back and take a look at every requirement that's in that spec to see if it's still complete and correct, exactly the way you described it, Ron. And people are lazy. They don't like to do that.
Right. It takes work.
That's right. It does. And when you do it, you actually get surprised. You discover that something you thought you knew from 20 years ago is not only obsolete, but it's probably incorrect.
Right. And this is why we have to validate requirements, not just generate them.
Bingo. And there's another comment that's kind of related to this, because you've mentioned it a couple of times here, is whenever I see adverbs and adjectives sprinkled inside of a requirement, that's usually a red flag.
Yep.
If you write a proper requirement, you don't need a lot of adjectives and adverbs.
Right.
I've worked on some documents where I could improve the document on first reading with a red pencil by crossing out about a third of the words that are there, because they don't belong there. They don't contribute anything to it, and they actually create revenue for lawyers when the project goes to litigation.
Yes, and the training I did for Boeing when I was there, I said adverbs and adjectives are not your friends. So get rid of them, because especially the adverbs, people use them as a substitute for performance value. And then we get the lawyers involved, as you said. Yeah, great comment. Thank you. Anybody else have a question?
Kind of have this is Jose Brund. I had a question kind of along something you just mentioned a little bit ago about kind of these higher level requirements. If there's any real value in having these type of requirements, where a lot of times the way you validate that they are passed is, if you say they're child requirements, you can validate those, and if you validate the children requirements, that means the higher level requirement is good. Is there value in that type of requirement, or
no?
Do you see?
If it's a requirement, that means it's got to satisfy the criteria, the who shall what, how well, under what conditions. So I go over this in the tutorial, but the short answer is there's no such thing as a high level requirement. Either it's a mandatory characteristic that's verifiable, or it's not. If it's aspirational, then don't write it as a requirement. Say, we want a system that has these kinds of characteristics to meet these missions or these goals or these objectives, and you write a description, and that's all good. And then you write requirements. The key about requirements is they are the functional performance requirements. They're tied to a system boundary. So regardless of what the level of your system is, whether it's system of system or subsystem or component, whatever, you find the boundary where the inputs and outputs are, and that's where you write the requirements. But the structure of the requirements is independent of the architecture level. The concept of high level requirement is an excuse for laziness, as far as I'm concerned. People don't want to spend the time doing the analysis to come up with the real numbers or investigate the interfaces. And so they copy from the last program or write these aspirational high level descriptions, put a shall in it, and think they've written a requirement. And it's not good engineering, because it institutionalizes ambiguity. And you can just imagine the arguments that you're going to have at system requirements review, critical design review, verification review, functional configuration audit, first article inspection, or what does the requirement mean and how does the design satisfy it? So I would say have the argument about what the requirement means at SRR, and then fix the requirement so it's verifiable. So I don't know if we need to stop, Ray, or
Hello? Can
hello.
you hear me? Yes.
Yes.
Okay.
Okay,
Great.
Devia.
Are there any final questions for Ron? I know we've gone over a little bit, but okay. All right, since I'm not hearing anyone chime in, I just want to thank Ron for a great talk. Obviously, we learned a lot and there's a lot of questions. So thank you very much for your time and for presenting. And thank you everyone for participating today and to our general membership meeting. There was a question that came up regarding the slides for this evening's presentation. So if you would like a copy of the slides, please reach out to Jim Brown and he can get a copy of those over to you. And if that's it. Yes.
Yeah, and let me just say, I will post, as soon as I get the video, I will post that in my YouTube channel so you can listen to me again if you're so inclined.
Great, awesome. All right, and with that, thank you everyone for
Thanks, everybody,
for participating, and enjoy the summer, and we'll see you all back in the fall sometime for our next meeting.
Thanks very much.
Thank you.
Thanks, Ron.
Bye. probably want to stop the recording, Devya.